we didn't do this in class today, but I'm going to assign it anyway because really what's going on is just a vector problem. What we're going to do here is look at a mass. We can see MA. And let's pretend it's hanging from a string. And let's pretend that that particular string is connected to two other strings. They're all tied together. And these other strings go and connect to the ceiling and to the wall. And so that this sign is just kind of hanging in what we call equilibrium, right? And we're going to call it static equilibrium because it's not moving. And we can see that those strings that are attached to that knot in the middle there, that central knot, they have angles, right? So we'll know those angles, 45 degrees and 36.9 degrees. And again, this is going to be called equilibrium or static equilibrium. Static just means, again, it's not moving. Okay, so static is important because, we know that if I'm in quote-unquote equilibrium, I could be moving at constant velocity. Well, I'm going to make very clear that this is not moving. We're in static equilibrium. And so let's assume that this hanging mass is 10.2 kilograms. That's an easy mass because that makes the hanging weight 100 newtons, right? You can verify that. 10.2 times 9.81, it's 100 and a little bit, but basically 100. And the question is going to be, well, what's the tensions in those strings? What's going on with those tensions? And what we need to realize is that this just is a glorified vector problem. What we can do, I didn't want to do that. What we can do is we can redraw that knot, that central knot. That's going to be our place that we want to focus on. So a lot of people are like, well, wait, don't I draw a free body diagram of the mass? And these particular kinds of problems, no, actually, you want to focus on the knot. That knot is the central point where all the forces are acting. Right? You have three forces. You have the force acting downward. You have the force acting downward of that mass. Now, it is true that really this tension is equal to the tension on the mass hanging upward, but they're equal at opposite tensions, and that's going to be equal to the gravitation of the mass itself. So there's a bit of a daisy chain there. That is absolutely true. But since the rope is so short, we're basically going to say, that mass is almost directly connected to that central knot, and so we can make that estimation. So I said, all right, that tension in this short little line is going to be basically equal to the gravitation of that hanging mass. And I can say that because we're not accelerating, right? We are not moving. We're in static equilibrium. So that's cool. I actually know that I can figure that out. I know that that's value, but I don't know the tensions in these two strings. And the question is, well, how am I going to find those tensions? Well, it becomes a vector problem. And it becomes a vector problem where the resultant is zero. We don't want a resultant. We don't want this thing to move. And so one of the first things we need to do is we need to talk about the components of those two vectors that are angles. And so I already have it kind of pre-done. And I'm going to say, well, look, what are the components of these vectors? If we happen to know one of the sides, we know the angles, then we can figure out a bunch of other things. But we don't happen to know any of the sides of any of these hypotenuses or legs of these triangles.